Factorizing polynomials is an important step when you want to do partial fractions, which is important for integrating rational functions. So if you master factorizing polynomials, a lot of things become easier, especially in integrating big fraction things. So if you have a polynomial with real coefficients, so intuitively it's just your normal x cubed, x squared, things like that. So for example, this is possible. This is a polynomial with real coefficients. All these numbers are real and it's a polynomial. So when you see a polynomial with real coefficients, you can factorize it into linear terms. So linear terms being, this is a linear term. Let's suppose x is a variable, and then the x can only appear as an x, and x to the 1, which is x, or x to the 0, which is a constant. You shouldn't have any other powers of x around here. So you can factor it into linear coefficients or quadratic polynomials. I'll show you an example right here, just to show you what I mean. X to the 4 minus a to the 4. How can we factor this, what's this called? Quartic polynomial, because x is to the 4, so quartic. The trick here is to notice that x squared minus a squared, so this is a difference of 2 squares. If you're not that sure, you can substitute u equals x squared, v equals a squared, then x squared is u squared, minus a squared is v squared, and directly apply the formula you've probably been forced to memorize by a math teacher. Ta-da! Substitute x squared, a squared in, and we get this. Alright? So these are two quadratic expressions, but we can go a bit further because the second brackets is also a difference of 2 squares. Very simply, we get something like this. So this is what I mean. All polynomials, all of these, they can be factored into, these are linear terms, and also quadratic terms. Now, why is that the case, you may ask? The reason is not that complicated actually. So this is going to be a bit of theory. You can skip it if you like, but if you want to know why, we can factorize all polynomials very simply. Then here's the reason. So if we have a polynomial and we want to factorize it, let's say we want to Let's not think about factorizing for now. Let's just think about dividing it by x minus x naught. So what we mean by dividing? If we want to divide 47 by 7, 6 times 7 is 42. 42 plus 5 is 47. So, right? 47 divided by 7. This is how you normally write it. 47 divided by 7 equals 6 with a remainder of 5. This is what it also mean, right? That 47 is equal to 6 lots of 7 and the plus a remainder of 5. So dividing a polynomial by, let's say, this linear polynomial is also the same method. We have the polynomial to be divided here. I'll give some numbers so that it makes sense. It makes more sense. So let's say we want to divide it by x minus 1. What it means is that we want x squared plus 3x plus 2 to equal x minus 1 multiplied by the quotient, right? Quotient plus the remainder. This looks super complicated probably because it's a px, qx. Don't worry, px and qx are the, like, you divide a polynomial already, you get another polynomial. So these px, qx, the quotient, remainder, maybe I should put it that way. Quotient, remainder, they should be polynomials. So just think of them as polynomials that we don't know their coefficients. Anyways, how do we get q and r? Substitute x equals 1. Because both sides must be the same x expression, you substitute x equals 1, both sides must be still the same. So x squared plus 1, okay, x squared, 1 squared 1, 3, 2, this becomes 6. Now why we substitute x equals 1 is because now we put in 1 here. 1 minus 1 is 0. Q of 1 times 0 is 0. We got rid of the q. R of 1. What we get now is that the remainder is 6. Well, you may ask, okay, but R might be like a linear factor. It might be quadratic. But here, because it's a bit like saying 47 can also equals 5 times 7 plus 12. That's also perfectly valid. But we want the smallest remainder, right? Here we want the r to have the smallest, or x power. So since we want r to have the smallest x power, 6 equals rx. Let's just suppose r equals 6 for now. And then let's see if we can find the q. Since this is the smallest possible r with the smallest possible degree, polynomial degree, meaning that x, the power here is the smallest, we need to find q now and see if it's possible to find qx, or else we may need to change our remainder to a high degree polynomial. Okay, enough of me just waffling around. Let's do the math. Okay, then let's divide. Or rather, I'm going to try to find qx. I'm using the long division method that I've shown in the other video earlier that I've posted on YouTube. I don't know what it's called anymore, but whatever. Oops. This should be one. I apologize. There we go. So left hand side expression is equal to x minus 1 times x plus 4. So if we let qx equals x plus 4, then let's see if everything works out. X squared plus 3x plus 2 equals x plus 4 times x minus 1 plus 6. Indeed, that is correct. You can check by expanding. Yeah. So what we have here is now a divided form, like this one, where the remainder is as smallest as possible. Here the smallest as in the idea of the order of the polynomial is lowest, right? The degree of the polynomial, sorry. So that is division. And we can actually divide by a root of the polynomial. A root of the polynomial is, okay, we have the polynomial here. A root is a number such that you substitute the number into the x, the polynomial becomes 0. So this is like a number. It makes this expression 0. An example will be for this particular polynomial be minus 1. 1 minus 1 square is 1, minus 3 plus 2 is 0, right? So now, if we were to try to divide x squared plus 3x plus 2 into this form, actually, what do we want to divide by? Minus a root. This is a trick, right? Why? Let's look. I should make it clear that we're putting minus 1 because we want minus of the root, right? So let's get rid of this. This isn't all working. Now we want this dividing now. Substitute x equals 1 in x equals minus 1 again. You get 0 because minus 1 is a root. This one, what will become? Minus 1 minus minus 1 is 0. So this also becomes 0. And we have r of x. Now r of x, let's let it become 0. Right? Because that's as small as possible. It is the polynomial with and that satisfies this equation, plus it has the smallest degree. So r x becomes 0 if we were to divide by x minus a root. So this is what happens. When you divide a normal polynomial by its root, you will literally factorize it out. You will have no remainder. Gauss has a theorem. It's called the fundamental theorem of algebra, although it is probably neither fundamental nor algebraic. It's more complex analysis stuff. The theorem says that all polynomials have at least one root. All polynomials with a degree of 1 or higher, so like an x or an x squared. Now what happens, right? If it has at least one root, if a polynomial has at least one root, we can factorize it into another polynomial. Now this other polynomial that's inside here is also a polynomial, so it has a root again by this theorem. So you can again factorize that to get, it's probably something like another polynomial that's smaller, or it's pretty more simpler because you're dividing. This one also has a root by this theorem, so we can factorize it again and again and again, pulling out linear factors until we get it totally factorized. Here, our polynomial has real coefficients. However, some polynomials may have complex roots, right? Well, this one will have a complex root of a times I, or minus a times I, for example. Now we can factorize this into like this. I should clarify that if you use this, if you work out this theorem, all polynomials can be factorized into like factors of x minus a alpha naught, let's say, or just alpha, where alpha is a root of the polynomial. So a polynomial, you can, actually I'm not sure, something like this, right? Oh, okay, forget it. It's okay. So just any polynomial, you can write it as this way. A bunch of brackets, each one having, well, it looks like x minus a root. Then the other bracket will have x minus another root, and x minus another root. And you times a constant at the front to account for the constants in front of the biggest power. But all polynomials, you will be able to factor into this form, right? Constant times x minus its root times x minus its another root times, and so on and so on. So that is a theorem. Finally, here though, if we have a polynomial with real coefficients, complex roots come in conjugates. So if z0 is a root, then the conjugate is also a root. I've explained this in another video I did on my YouTube, but suffice to say, if we have something like this, oops, we get the polynomial, we divide it, and okay, we have these two factors, of course. Let's multiply them together now. Complex number plus its complex conjugate is a real number, and the complex conjugate times its complex number times its conjugate is also a real number. So what we have now is that this expression can be turned into brackets, factors, inside of which there can be linear terms, x minus a real coefficient, a real root, or it can be a quadratic expression like this, but it also has real coefficients here, here, here. So now the theorem becomes a polynomial with real coefficients can be factorized into factors of linear quadratic terms with real coefficients. Now this is going to be super useful because if we can factor any polynomial into those linear quadratic terms, we can partial fractions, and using partial fractions method, we can get fractions with very easily differentiable denominators, just linear and quadratic terms, so using logarithms and arctangents. Very, very simple. So not simple, but this process becomes just it's just a bunch of steps that you can follow through without thinking. So there isn't like, you don't need any massive intelligence. It just turns into book work. But that is still a pretty big step, right? You still can do the thing. Okay. So now that is all the explanation out of the way. Let's do some more examples. Let's try the second one. X to the 4 plus a to the 4. How do we even factorize this thing? Well, first things first, we probably want to find its roots, because if we can find its roots, we can write it in this form. This is a root, x1 is another root, 2 is another root, right? And then if we find all its roots, substitute all of these roots in here, substitute this, and then we can multiply the factors with complex conjugate roots together, and we will get the expression that we want. Sounds very complicated in theory. In practice, it's much easier. I'll show you why. I'll show you how. If you know your complex numbers, then let's try to find roots of this guy. It's minus 1. X equals minus a to the 4, 1 over 4. that is one possible root. Minus 1, 1 over 4, a, that is one possible root. Minus 1 equals e to the I pi. That is its exponential form. E to the I pi over 4. We're just using indices rules. Then e to the I pi over 4, e I theta equals cos theta plus I sin theta. I shall not write it in that Cartesian form yet, because this has its advantages later, but this is a possible root. We multiply this by, okay, what is, how's it? So minus a to the 4, 1 over 4 is also a root. Let's start from the beginning. I apologize. So x to the 4 plus a to the 4 equals 0. X to the 4 equals minus a to the 4. X equals minus a to the 4, 1 over 4. So we raise everything on both sides to the power of 1 over 4. And this minus a to the 4 times 1 does nothing, right? But I like to write it like that, so that we can do 1 over 4 power on both sides. I apologize, it's kind of early in the morning. So we can do this. E 2I pi over 1 over 4 is another root. So this is another root, right? And if you use 1 equals e to the 4i pi, you will get another root, and so on. So this is just my method of finding the roots of unity. You probably don't have to follow me. I just like to show my method. Anyways, if you know your complex numbers, these will be the numbers. These will be your roots. Okay, just double checking with my old working, I've done it right. So x to the 4 plus a to the 4, we write it in this form, equals x minus a root, x minus another root, x minus the third root, x minus the fourth root. And then if we expand all the exponentials in the Cartesian forms, we will have it factorized. But this isn't complex numbers. Why not we get them in real coefficients? So we move the factors around a bit, because this and this, they are complex conjugates. And then we multiply them together. Let's get this first, and then we multiply into here. It's just a bunch of maths, big expressions. This one also we multiply together to get a bigger bracket. And so we can simplify it. This becomes this, and this becomes this. If you want to check yourself, I'll let you do it. Here you go, pause the video. Alright. So we get this. Whoa, what just happened? How do we get this? Is this equal to this? Indeed it is. I won't do the expansion because it's quite a lot of work, but it does work. This is what happens. And this is what I mean by all polynomials with real coefficients can be factorized into factors with factors of quadratic or linear terms, and all these terms have real coefficients. This is a real coefficient, real coefficient. All of these have real coefficients. This is also known as the Sophie-Germain identity. By this lovely looking lady. Oh, there's no E in the back. Sophie-Germain. There we go. Her identity. Well, her original one has a 4 in front somewhere here. Constant, but it's close enough. So there, that was quite unexpected. You probably will have never guessed that these two polynomials are factors of this. But can you see, like, the method is very straightforward if we can find its roots. We find its roots, and then we can immediately factorize it into this format. And then we expand the brackets, combining complex conjugates together, and we will get the factorized form. Let's do some more practice. Just to illustrate what I mean, here you go, this is another one, x to the 6 minus a to the 6. Well, why not use difference of two squares again? It served as well. And now we use some, okay, we have these two factors now, x cubed plus a cubed, x cubed minus a cubed. If we can find each polynomial's roots, we can factorize it yet again, multiply together the complex conjugates. So that is more roots of unity things. Here's my working. And so we find that actually the first one, okay, x equals minus a is a root. So we can divide this by x plus a. There we go. This one we cannot factorize it anymore because we will get complex factors, coefficients. Sorry, this is a. So this factor becomes like this. Ta-da. And how about the second factor? Second factor, x equals a is another root. So let's divide by x minus a. X minus a root. There we go. This again, this quadratic factor, we can factorize further or else we will get complex roots. So that isn't that bad, right? Boom. We can factorize this order 6 called polynomial into quadratic and linear terms with real coefficients. Right, let's try one more beast to just show you that we really can factorize any polynomial. So this looks terrifying again. We can't use difference of squares. We probably don't have any ideas in our head right now. So the most straightforward thing to do is to blast it open using your roots of unity and complex numbers things. Now where's my working? So this one is going to be just, we try to find its roots. Doing the heavy maths, we get this. Now I just want to point out a bit that it's probably more convenient if it's something like this to write. Okay, we have all the roots here, right? And then this one, this root here is a complex conjugate of this root here, so we want to multiply them together. But instead of writing it as e to the 11I pi over 6, write it in this form, e to the minus I pi over 6, to make it more clear that these two are complex conjugates, because there's a minus in front of the I here, that's it, right? So this and this we combine together, this and this we combine together, and this combine together, that's fine. And then we multiply them out together, noting that if we have this, e to the I pi plus e to the minus I pi, write it in Cartesian form. That's equal to 2 cos theta. So the math works out pretty nicely. We get this. We can't factorize these quadratics anymore, because they all have, if you try to factorize them even more, you just end up with these things, all these roots, and they are all complex, which we don't really want. We want them all in real coefficients. So there we go, yet another one done. It isn't too bad, right? It's quite straightforward.